Hey, before we go on to a new topic, I want to review double slit diffraction for you. So I've got this system where somehow I have monochromatic light coming in here, and let's say it's probably red because the diffraction will be greatest. Remember, diffraction is greatest when the wavelength is big compared to the opening, and that's why Newton wasn't able to see the diffraction nature of waves and light, because come on Newton, fix your bow tie. The waves of light are so small, and Newton wasn't able to make accurately really tiny openings in order to see that, and he didn't know that wavelength dependence fully, so he was unable, well, he really didn't know much about light at that point. Okay, but he did stick needles in his eye so that he could learn, so that's cool. Bye-bye. All right, if we have monochromatic red light coming through these two slits, we can define a couple things. Let's define the distance of separation between the two slits to be d. Good. And the width of the slit doesn't particularly matter at this point, of course. It will in a little bit, but we're going to say that it doesn't. And then I need to know what sort of thing is resulting from this setup. And a very long way away, I've got a screen. And this is a place where the light can fall, and I can actually look at the brightness or the dimness of the light falling on here. And I guess you would predict, even if you didn't know anything about diffraction, you would predict that there would be more brightness in the middle by where these two slits are, and less brightness on the far away. Maybe your most basic prediction would say there's a lump here right in front of this, and there's a lump here right in front of that. So I'm going to draw these lumps as representing the brightness of a particular region. So you might make a prediction where there's like brightness in the middle right in front of these guys and not as much brightness. And it turns out there's also interference, and we've got these bright maxima, so there is a bright maximum that's right smack at the center, and that's because there's no wavelength difference between a ray coming from here and a ray coming from there. Remember, by, oh man, I'm not going to be able to say his name, Huygens principle, there's the exact same distance here, and each of these is a point source. So that makes constructive interference here, and I'm just going to say there's another region of constructive interference here and here. So this is m equals 0, m equals -1. We're going to do this same flavor when we get to quantum mechanics. So get a feel for these m's. They're pretty cool. -2, -3. They're just a way of ranking. M is really just an integer, and it allows us to sort of scale what we've got going on and to keep things in order. But the screen is not bright right in the middle and dim over here and dim over there. It's got much more interesting structure of brightness to it. So this I'll call the envelope, but there's also a bright fringe right here. Let's see if I can draw that. What should we do, purple? Sure. So the brightness really looks like this. There's a bright fringe right here. And then it must be perfectly dark in between those, and another bright fringe right here, and another bright fringe right here, and another bright fringe right there, and it actually goes on, but the intensity of these guys is falling off. I'm getting further away from the source, and so the energy coming down here very far away at very high or very low m values is going to be very small. So I'll put another peak right here, and another peak right here, and another peak right there. So what is shown in purple is actually the pattern that you see if you look at it. So you'd see, if you looked at it, you'd just see bright, slightly dimmer again, but in between these bright spots, you'd see dim spots. So there are some equations that we got from this. First of all, I'm going to say that this distance is L, and in double slit diffraction we said that if d times sine of theta, well, that's going to be the path length difference between one slit and the other slit. If that is some integer multiple of the wavelength, so that's this statement where m is an element of the set of integers. If it is an integer, then we have bright fringes. And of course, if it is a half integer, then we have dark fringes. But wait, we can also say some simple geometry. Simple geometry gives us that y, now that would be the spacing between here and here. I could say the separation between the fringes. Now you know that depends on the angle, but it also depends on how far away we are. So if we're very far away, then we can expect y to scale as bigger as we move further away. we have to know, we're making the implicit statement that L is much greater than the slit separation, and it's also much greater than the wavelength, which is supposed to be greater than the slit separation. Yeah, so we've got a very, very far away screen when we're doing this, but we're going to say that it's going to be L times the tangent of theta, and that's some simple, simple geometry. You can do it! Now, you're not going to like this, but I need to tell you that if I have monochromatic in-phase light coming to a single slit, watch this, here it comes. I'll give you a purple wall. And I'll give you, well, we're gonna have to zoom in on it a little bit, but I'm gonna just draw a sketch of what we've actually got. We've got monochromatic light coming in here in phase and all lined up nice and pretty. There is just one slit, and while you would be expecting something like this, here's the screen, you are probably expecting a lump of stuff that you can see. Where am I going to draw that? Like this. You're going to say it's bright in the middle and dim on the outsides. The problem is that even a single slit, the light interferes with itself. This is like, well, I'm going to call this self-interference. And this is like you're in a conversation, interference. Wow. Self-interference. And this is like you're in a conversation with yourself. You're talking to yourself, and sorry, you get interrupted because you just got a text from yourself. This is very weird. I'm going to define this distance here as the width of the slit, W, and I've still got this same distance down here that I'm defining as L, and it's not this. This pattern does not emerge. It is the envelope for what does emerge, but we get this funkiness on top of it. I'm going to get this, and then this, and that, and that, and this, and that, and that. Wow! You get diffraction from a single slit. So, I don't know, I mean, maybe this is the first time in physics you've really said, Dr. Schuster, are you sure about that? And yeah, unfortunately, I am. So watch how this happens. We need to make that assumption again where L is much greater than the slit separation. Well, we're going to call it W in this case because it's not really a slit separation. It is the slits with itself. And I'm going to say that if we zoom in on this particular slit, we can say that the slit is actually, whoa, now it's really big. The slit is actually 2 slits. Really? Yeah, because I'm gonna put a little red dot in the middle. Ha ha ha! Now it's 2 slits, and I can put a dotted line out this direction, and I can say that there is a point somewhere out here, very far away, where a ray coming out at a certain angle here, theta, this ray I'll call ray 1, will interfere with the ray coming out at that same angle here, theta, and in fact be exactly half a wavelength out of phase. So all I need to do is I need to drop a normal line down here. Watch this. Dot, 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 dot. And I need to say that that's the right angle, and I need to look at this distance right here. You want to guess what that distance is right there? Well, it has something to do with the slit separation, but wait a second, this just one slit, it's not separated. Well, no, look at that dotted line there. There are 2 slits. And what is the separation of the 2 slits? Well, here's one slit and its center is right there, and here's another slit and its center is right there, and the separation between those 2 slits, why, that's just W over 2. Wonderful. So I'll draw you a little dotted line right here and pull out a bracket, and I'll say the separation of the 2 slits is W over 2. So where we previously had D times sine of theta is going to have to be m times lambda for a bright fringe, and d times sine of theta is going to have to be, well, I guess, what was our first dark fringe? It was 1/2 of lambda. This was our first dark fringe. Now I'm going to watch this. Now I'm going to say that the separation of the slits, there's one slit, but it acts like two slits. The separation of the slit, wait, can I define this distance here? Sorry, I was leaving off there. We actually should write down what that is right there. And that looks like W over 2 times the sine of theta by some very simple geometry and trigonometry. And, well, I'm just going to plug that in for D. That is what D was in our previous development, and we're going to say W over 2 times sine of theta is equal to 1/2 of a wavelength for a dark fringe. Check this out. That's a dark fringe, yo. If that's a dark fringe, then we can cancel out the halves, and you're about to see something that you're not going to like at all. You really are not going to like this. It says the width of the slit times the sine of theta is equal to lambda, or I guess we could put an m lambda in there. No, we haven't justified that yet. But I just do want to say that this looks like a bright fringe in that circumstance. But remember, the D is actually half of the width of this single slit, so we get the half canceling out, and this is a dark fringe. Make special note of this. Are you taking notes? What are you thinking, to just sit back and eat popcorn and learn physics? No, you gotta take some notes, you gotta do some problems. Now, that's all well and good because this ray number 1 here interferes with that ray number 1 right there. But I could point out another set of rays that also interferes in the same way. These rays are going the same place. They are going to your eye, which is said to be so far away that these two parallel rays will both meet there. That's the essential statement that the screen is very far away. But I will point out that this other ray, which I choose to be just a little bit below this one, is going to interfere with this ray, which is just below that one. So this is ray 2 interfering with that ray 2 as well. We've got interference the whole way down. Look at this ray right here, which I could call 3. It's interfering with this ray here, which I could call 3. Yeah, it really does self-interfere, and there really will be a dark fringe. And look where the dark fringe is. Now here's the issue. You want to figure out what's going on first? Let's do one more thing. I want to say, oh, here's another one. This one, ray 4, I guess, is interfering with ray 4 down here. Oh, wow. Now, we've already said that a single slit is actually two slits, but I want to blow your mind perhaps a little bit further. We'll come back to this slide, though. I want to blow your mind perhaps a little bit further, and I want to point out to you that this slit of width W that we've already been studying is in fact 4 slits. Watch. I'll put a dot in the middle, and I'll put a dot here, and a dot here. And the width of each of these slits is W over 4. That's how wide those slits are, and it's also how far apart they are. So that's W over 4 there, and I can also put a little dotted line between here and here, and the slit separation is also W over 4. See how neatly that works? Now we have 4 slits, and those 4 slits are interfering with each other. I told you you were not going to like this, and I give you a ray right here and a ray right here. You ready for those 2 rays? Those 2 rays are parallel because they each have the same angle right here, and they interfere with each other because they are not the same path length. If I drop a normal line down here, tell you that it's a right angle, and analyze this distance right here, I will find that distance to be W over 4 times the sine of theta. And that means that we can conclude, wait a second, we'll get another dark fringe if W over 4 times the sine of theta is 1/2 lambda. That's another dark fringe. Remember our previous dark fringe? That was when we treated the single slit as 2 slits. But now it's actually 4 slits. And I suppose we could also treat it as 256 slits. And so we've got this beautiful pattern of splitting it up into as many slits as we possibly want, and we're going to get dark fringes as a result of interference between the various slits, which are comprising the main slit itself. There's just one slit, but really there are an infinite number of powers of 2 of slits. Here we go. I'm going to look at what happens here. In this case, I can say that W times sine of theta is... Oh, sorry, I was going to summarize our previous results. I got carried away there. Oh, I'm so sorry. 1/2 lambda. This gave us a dark fringe, and this gives us a dark fringe also. I'm going to take this equation right here and just multiply both sides by 4. I get 2 times lambda in that case, and remember, that's a dark fringe. So remember, like, here's what I'm deriving. I'm saying that W times sine of theta, if it's any number times lambda, as long as that number, let's say that's got to be a natural number or something, as long as it's 0, 1, or 2, wait a second, 0? 0 going to do it? No, 0 is not going to do it. It's got to be a whole number. There, the flying W. If it's a set of the whole numbers, that is m equals 1 or 2 or 3 or 4 or something like that, then we're going to get ourselves a dark fringe. That's incredibly powerful, and now I just want to wonder, what does that bright fringe in the middle look like? And we drew it a little bit interestingly. I want you to notice that this bright fringe has a certain width. And I want to figure out what the width of that bright fringe is. I'm going to call it delta y. I'm going to put kind of delta y in parentheses, in quotes, sorry. Remember, we could say that delta y is L times the tangent of theta, approximately. Now, the thing is, we need to know the separation in angle between the first 2 dark fringes, like the dark fringe that's up and the dark fringe that's down. So let me get those dark fringes for you. I've got a dark fringe where this equation is satisfied, and I've got a dark fringe where this equation is satisfied. And that means that the angle separation is really, well, you guys remember that if theta is really small, then I know that the sine of theta is pretty much the same thing as theta, right? So I can say that W times theta is equal to lambda all the way to W times theta is equal to negative lambda is bright, because dark bounds the brights, and I'm going to say all the way from this angle to that angle. So theta can go, well, I guess I've got my range of theta that I can have, which is 2 times lambda. Let me check my notes right here. Is that true? Yeah, it's 2 times lambda divided by the width. So if I want to look at delta y, oh my goodness, if we're considering the situation where theta is much, much less than 1, sine of theta is about theta, well, guess what? So is tangent of theta. It's also just about theta. What fun. So we can be super sloppy, and we can say that delta y, the width of the first slit, is in fact L times 2 lambda over W. And that's twice as wide as every subsequent spacing. This is twice as wide as that one, and 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 that one. Because it's a single slit, it has that one distinct difference from a double slit experiment. That is, frankly, all I have to say about that. And I'm sorry that I made you consider a single slit as if it were 2 and 4 and 8, etc. Goodbye. Can fall, and I can actually look at the brightness or the dimness of the light falling on here. And I guess you would predict, even if you didn't know anything about diffraction, you would predict that there would be more brightness in the middle by where these 2 slits are, and less brightness on the far away. Maybe your most basic prediction would say there's a lump here right in front of this, and there's a lump here right in front of that. So I'm going to draw these lumps as representing the brightness of a particular region. So you might make a prediction where there's like brightness in the middle right in front of these guys and not as much brightness. And it turns out there's also interference, and we've got these bright maxima, so there is a bright maximum that's right smack at the center, and that's because there's no wavelength difference between a ray coming from here and a ray. All right, if we have monochromatic red light coming through these 2 slits, we can define a couple things. Let's define the distance of separation between the 2 slits to be d. Good. And the width of the slit doesn't particularly matter at this point, of course. Will in a little bit, but we're going to say that it doesn't. And then I need to know what sort of thing is resulting from this setup. And a very long way away, I've got a screen. And this is a place where the diffraction nature of waves and light, because come on, Newton, fix your bow tie. the waves of light are so small, and Newton wasn't able to make accurately really, really tiny openings in order to see that. And he didn't know that wavelength dependence fully, so he was unable, well, he really didn't know much about light at that point. Okay, but he did stick needles in his eye so that he could learn, so that's cool. Bye-bye. Hey, before we go on to a new topic, I want to review double slit diffraction for you. So I've got this system where somehow I have monochromatic light coming in here, and let's say it's probably red because the diffraction will be greatest. Remember, diffraction is greatest when the wavelength is big compared to the opening, and that's why Newton wasn't able to see